here's how to extract information off a graph. This is just going to be the basics, not a lot of talking, just where do I get the information I need to figure stuff out? Okay, what can we figure out from this graph? First, note that the vertical axis is position, the horizontal axis is time. We can determine that the amplitude of this graph is 5 centimeters. We can determine that the period of this graph is 4 seconds. Let's assume we're given the mass of the oscillator is 1 kilogram, just to make things a little simpler. We know that omega is 2 pi over t. So using that and the fact that t is 4 seconds, which we extracted from the graph, omega is 0.5 pi radians per second. We know the maximum energy, or the total energy, of the graph happens when the spring is fully stretched or fully compressed. It's fully potential energy. When it's passing through x equals 0, it's all kinetic energy. And so a great way to find the E total is by noting that it's going to be equal to 1/2 times k times a squared, where a is the amplitude at the points where it is fully stretched or fully compressed. Unfortunately, we can't figure that out until we figure out the k, but remembering that omega is equal to the square root of k over m, we can put in 0.5 pi radians per second equals the square root of k over m, and that would be 0.5 pi squared, which equals approximately 2.5 newtons per meter. Coming over here, I can calculate my total energy as 1/2 times 2.5 newtons per meter times the amplitude squared. 0.5 times 2.5 times 0.05 squared is 0.003 joules. So, coming back to the graph, when I'm at maximum amplitude over here at point A, not to be confused with amplitude, that's just point A, my energy is 0.003 joules of potential energy. As I come down and pass through the resting position of the spring, there is no more energy stored in potential energy because I have no stretch or compression. It's all kinetic energy at that point, but equal to 0.003 joules of kinetic energy. So at point B, I have all kinetic energy, and so 1/2 m times v max, my maximum velocity squared, is equal to my total energy. And so 0.003 times 2, take the square root, I get my Vmax equals 0.08 meters per second. That happens when the oscillator crosses through x equals 0. My maximum kinetic energy happens at the endpoints of the oscillator, which I'm showing on the diagram. And then somewhere in between, like where I've put this x over here, you're going to have the same total energy, 0.003 joules, but it will be a mix of kinetic and potential. And seeing as you can read the x position off of the graph, you can always figure out 1/2 kx squared and then subtract to get the kinetic energy at that point. All right, so we're making good progress. Let's write the equation for this harmonic oscillator. I'm going to do that over here. We know the general form for x of t is equal to a cosine of omega t plus phi. Let's examine this at t equals 0. We get that x of 0 which I already know is equal to the amplitude because it's at the amplitude at x equals 0, at t equals 0. So that's A equals A cosine of phi, because when t equals 0, the phase on the inside is just phi. Well, that means that cosine of phi equals 1, and the only way for that to happen is when phi equals 0, which makes sense because this is a pure unshifted cosine graph. And so x of t is equal to A, which is 0.05 meters, times cosine of 0.5 pi t. We can also write equations for v of t and a of t just by taking derivatives. I'm not going to do that right now, but that's our equation for the position as a function of time. All right, let's, as a final step, connect this to real life. Let's say I have this oscillator, and I'm going to actually come back to my graph. I'm going to erase all of this business. Here it goes. I'm also going to erase this because I don't need it. And I guess I'll leave that. I'm going to write my function over here, x of t equals 0.05 meters cosine of 0.5 pi t, just so I know. I'm going to label some points on this graph in red. Point A is going to be where we start. Point B is going to be here. Point C, point D, point E. And now I'm going to draw a harmonic oscillator. Let's assume this is 0, the unstretched length of the harmonic oscillator. And let's assume I can stretch it to the right. Let's say this is the positive direction to x equals a, and it could come down to x equals negative a. So if I'm starting at point A, not to be confused with the amplitude, point A, if I look at my graph, I'm starting at the maximum positive displacement. So this is actually, I'll do it in red so it coordinates better. This is actually point A. So I start here, fully stretched in the positive direction. From A to B, I move towards 0. So I'm moving in the negative direction. That's consistent with the fact, if you take a moment to look at the velocity graph, that my slope of the position graph is negative, so I'm moving in the negative direction. As I pass through point B, I then continue to move in the negative direction until I get to the maximum compression point C, where I stop again, which you can see by noting that the velocity is 0 at that point. Then I begin to move back towards point D, which is again passing through x equals 0. But now note that the slope of the velocity graph is positive as I move in the positive direction, even though my position is still negative because it's to the left of x equals 0. And then I continue to move in the positive direction back to point E, which puts me one cycle later at the point of maximum compression. And note the slope of the velocity graph is still positive, decreasing, and eventually becoming 0. So at these endpoints, v equals 0. At the midpoint, when it's passing through the unstretched position, v equals v max. Here, it's all spring potential energy. Here, it's all K. And somewhere in between, it's a combination of K plus U. I hope that was helpful just in terms of deconstructing a graph, helping you see how to pull information off of it, and I think this will help you with the AP classroom problems.